It's my pleasure now to introduce Ramin Raziperchikolaei from UC Merced. His work is about an ensemble diversity approach to binary hashing. Thank you.
Hi, I am Ramin Raziperchikolaei. In this presentation, I want to talk about binary hashing, and I will show you that we can learn good hash functions using diversity approach. First, I want to start with problem definition. In large-scale image retrieval problem, we have a large database of images and a set of query images. For each query image, we want to find similar images to the query among the images inside the database. So we want to find the k nearest neighbors of the query image, but it is going to take a lot of time because we have millions of images in high-dimensional space. What is a binary hash function? A binary hash function takes a point x in high-dimensional space and generates binary codes of length b for us. The main goal of the binary hash function is to preserve the neighborhood. So if 2 points are similar in the original space, a good binary hash function has to assign similar binary codes to them. If 2 points are dissimilar in the original space, a good binary hash function has to assign dissimilar binary codes to them. If we have a binary hash function, we can generate binary codes for the images, and then we can find the Hamming distance between them using XOR operation and counting, which are hardware operations. So we can find the Hamming distance between the points very fast, between the binary codes very fast. Okay, why binary hash functions are useful in large scale image retrieval? If we have a hash function, we can generate binary codes for the points in the data set and also for the query points. So we can find the nearest neighbors very fast because we only need bit operations to compute the Hamming distance between the binary codes. We can also save a lot of space and store all the images in the memory because to store one image, we only need b bits of memory. Many hashing papers first define an affinity-based objective function and then try to optimize this objective function to learn the good hash functions. To define an affinity-based objective function, first we have to define the affinity matrix, and the affinity matrix determines similar and dissimilar pairs of points. I have an example here. For the entry of the affinity matrix could be 1, then the points are similar. If it is -1, the points are dissimilar, and if it is 0, it means that we don't know the relation between them, or we want to make the affinity matrix sparse. The similarity can also be defined based on the labels of the point or their distance. After defining the affinity-based objective function, after defining the affinity matrix, we can define the affinity-based objective function. And I have the format of the affinity-based objective function here. The hash function is h. The output of the hash function is the binary vector of length b. And we have a summation over the pairs of the point. For each pair of the point, we want to minimize this loss function. When w is 1, means that the points are similar. So a hash function has to generate similar binary codes for them to minimize this loss function. I have two examples of the objective functions here. One of them uses Laplacian loss, the other one KSH loss, and many hashing methods try to optimize one of these two objective functions. And the loss function, for example, both loss functions try to preserve the neighborhood. For example, the Laplacian one, when points are similar, w is 1, so we want to minimize the distance between the binary codes. Optimizing these objective functions are difficult because the output of the hash function is binary, so we cannot, the function is non-smooth and we cannot take derivative. Most hashing papers define the hash function as the concatenation of b 1-bit hash functions. So h is a concatenation of h1 and hb, and h1 to hb are 1-bit hash functions. You can see that these 1-bit hash functions are all coupled in both objective functions. Here they are coupled because of this orthogonality constraint. Here they are coupled because of the square terms that we have. And optimizing the objective function was difficult from the beginning. When we have coupled hash functions, then it becomes even more difficult. Most of the hashing papers try to present new objective functions or new ways to optimize the objective function. We propose a new method. We propose to optimize each 1-bit hash functions independently. So it means that if we want to train B-independent hash functions, then we can train each of them separately. And it gives us several advantages. For example, the optimization would be simpler because we have B-independent problems over a smaller number of variables. Then we can get better accuracy and faster training. And obviously, the training can be done in parallel because we want to learn the hash functions independently. There is one important question: how to make sure that the objective functions are different. If we train all of the objective functions in parallel, it means that they could end up being identical and we gain nothing over only one of the hash functions. And we are going to use diversity techniques to overcome this problem. Here is the format of the 1-bit hash functions that we have. It is very similar to the Laplacian loss, except that it is much simpler. It doesn't have any constraint, and it is defined only on one of the hash functions. We use existing optimization algorithms, so it is not the focus of our work. But you can see that if we optimize this objective function b times, we can get b identical hash functions. And it gives us a trivial solution and very poor results on the image retrieval. And we are going to use the diversity techniques from ensemble learning literature to make the hash functions diverse. So we noticed that in ensemble learning literature, exactly the same problem happens. We have a training set, and we want to train several classifiers on the same training set. And if all of them are the same, then we gain nothing. So we are going to use the diversity techniques that I mentioned them here. Different initialization, we initialize each hash function from a random point, and then we can end up in different local optima. Different training set, each hash function can be trained on a different training set and different feature subsets. Each hash function is trained on a random subset of features. So if we use these techniques, we can ensure that the objective functions are going to be diverse, not different, not the same. And in our experiments, we call the different initialization method ILHI, ILHT for different training set, and ILHF for different features. It gives us several advantages. I already mentioned two of them. Now suppose that we have B hash, we already trained B hash functions. We want to train B plus 1 hash function. We can train one separately and add it to the previously learned hash functions. I have several experiments. One of them is comparing the mechanism, the diversity mechanisms that we have with the KSH state-of-the-art method. And you can see that our this is precision based off the as a function of number of points in the training set. And you can see that all of our mechanisms work better than KSH, which is a state-of-the-art. In our second experiment, we report precision as a function of number of bits. So we have our method, KSH, state-of-the-art, LSH is just random projection, and TPCA is truncated PCA. You can see that KSH stops improving the precision at B equal AT, but ILHT gives better results than all the other methods, and it also improves the precision hugely. Finally, we compared our method on CFAR dataset. We compared ILHT with the other hashing method on CFAR dataset. We report precision and recall, and precision as a function of number of points in the retrieve set. We can see that the red curve can beat other state-of-the-art methods. And to conclude, most of the hashing papers try to propose a new objective function, which is where all the 1-bit hash functions are coupled. We showed that this is not necessary. We can train the hash functions independently, and it gives us several advantages. The optimization is simpler, the training is fast, and we also showed that the precision of our hash function can beat a state-of-the-art, or at least it is competitive. We used diversity techniques to avoid the trivial solution, different initializations, different set of features, and different subset of points, and we showed that the last one works best. Thanks.
We have time for 2 questions. Any questions? Yes?
try it and how big it can scale?
I can't hear you, sorry.
Can you say anything about scalability of the algorithm?
About this case, most of the hashing papers, since the objective function is defined over the pairs of points, they are limited to a small number of points, a small number of pairs of points. For example, just 5,000 or 10,000. So most of the hashing paper is limited to a small number of points, but our paper, since it is training the hash functions separately, we can give different pairs to each of the hash functions. So generally, we can train over a much number of training points than the other hash functions.
Another question? No? Let's thank the speaker again. Oh, you're not Cynthia?
No, I'm not Cynthia. I'm Vitaly Feldman.
Okay. Okay.
Hello? Can you hear me? Oh, wonderful.
Now we have Vitaly Feldman from IBM Research, who will talk about generalization in adaptive data analysis and holdout reuse.
Thank you, and it's a pleasure to be here. So I will be talking about basically a new perspective on a very old problem in statistical data analysis. And this is joint work with Cynthia, Dwork, Moritz, Hardt, whom you heard earlier today, Tony Pitassi, Omer, Reingold, and Aaron Roth. So let me start with briefly reminding you sort of the basic setup of statistical data analysis, and I'm sure all of you know it, but I'd like to put under the same umbrella the kind of machine learning most of people here do here with the more classical statistical work in statistics. So OK. So in this setup, we start with a set of objects we want to know more about. It's very often it's people and their health, but it could be financial transactions or weather or whatnot. So the set of objects is usually too large, and we can have information about it all. So we get a data set, which consists of samples from that population. And we give this data set to some analysts who perform some either machine learning or statistics. From there, we get some results, such as parameter estimates, predictive models, classifier or clustering. And the main question we would like to understand is whether these results that we have learned on the basis of the data set will generalize to the underlying population. So this is exactly the generalization error you've heard about earlier in the case of machine learning. But in general, we want to know whether the conclusions still hold on the population. So how do we get those generalization guarantees? So one sort of standard way is to we have those generalization guarantees is that we start with some fixed procedure, such as hypothesis test, regressional learning, have some usually theoreticians who analyze those procedures and come up with some sort of theorem which says that if you feed fresh data, and fresh here means basically just independent of the procedures that we are analyzing, then you'll get some result. And for that result, you also have some generalization guarantees. That's given by some sort of theorem. And it could be, for example, a confidence interval for some underlying parameter. And confidence interval is exactly the relation between a statement about generalization guarantees of an algorithm. So in machine learning, so this is what statisticians have been doing for ages, and more recently people in machine learning theory. But in practice, we actually rely on different types of different way to get generalization guarantees. And this is sort of family techniques which we'll refer to as holdout validation. And it basically starts with this simple and very familiar idea. We start with all of your data. You split it into parts. That's not working. OK. So the first part is training data. The second is holdout or testing data. So on the training data, OK, something is not. OK, so on the training data, you run whatever learning algorithm you like, and and there are completely no restrictions, and you get some predictor out of it. Then you measure the error of that predictor on the holdout data. And as a result of this measurement, you get some sort of test error of this predictor. It's also very easy to see that if you make an assumption that the holdout data is in some sense fresh, then you'll also get generalization, some bound on generalization error of this hypothesis. So again, this could be some sort of confidence interval for the, I don't know, Okay, sorry, it's not quite working. Maybe I should stand closer. On the generalization error, you'll get some sort of constant interval on the true error of this hypothesis. So, and it's all very nice until we actually want to use the data more than once, and in which case the data is often already no longer fresh, and the theorems that we have no longer hold. Which brings me to the issue that I would like to discuss is that data analysis in practice is usually adaptive. And what we mean by this is that it consists of multiple steps, and each step depends, the analysis that we perform on each step depends on the results of previous analysis. So in the very simple case, we often start with sort of the simplest one with just 2 steps. We start with some data, we run some algorithm on this data, and we get some output from that algorithm, and then we use a different algorithm on the same data, but the algorithm can see the output of the second algorithm can see the output of the first algorithm, and as a result, it will depend, whatever the algorithm will be running in the second step will depend on the data. You can no longer think of data of this procedure as being independent of the data. So, and there are many ways in which such situations can arise. For example, exploratory data analysis, when you try to sort of first understand what's going on with the data. Variable selection routines are basically have this structure. Hyperparameter tuning, when you end up reusing the same data many times. And things like shared data sets, things which we use when we use, many groups use the same data set. Obviously, the next group learns from the things which have been done by the previous group. So these kind of data analysis, adaptive data analysis, it validates the guarantees that we have, generalization guarantees. But OK, maybe it's not a big issue. Maybe we can ignore it. But actually, there's plenty of published and folklore evidence that you can't just ignore these issues. In sciences, they cause a lot of problems. But we also know that in machine learning, it's very easy to overfit by not being careful. So what can be done? So let's say I really want my analysis to be correct, valid. So what can I do? If you look at the currently known theory, most of it can be summarized as abstinence. Basically, if you want to be safe, just don't do it. And basically, for example, in many social sciences, there is a strong push for so-called pre-registration, where you have to specify your complete analysis in advance before you get hold of the data. But we know this is one of those situations where abstinence only doesn't work. It's safe, but it does not work. So our goal is simply make it safe, just because, OK, people will be tempted to not abstain. So let me just briefly mention what kind of techniques we show that there exist techniques which can be used in this sort of adaptive setting. And the first technique is based on differential privacy. It's a notion of privacy, but privacy in this case is not very important. What's important is that it's a notion of strong stability in the probability space of outcomes. And for us, an important property of it is it preserves generalization, means that if you analyze something with differential privacy and use the results of that analysis, then subsequent analysis will still generalize. And it also composes in this adaptive setting, meaning that if you use 2 algorithms which are differentially private, their composition will be differentially private. And this is one of the properties that the usual notion of stability does not have. So we use this technique. We also show that quite a bit of mileage can be obtained from sort of the classical description length-based techniques. That also has this property that if your algorithm doesn't output too many bits, then it will not affect the generalization of the subsequent procedures, and also composes nicely in the adaptive analysis. On top of this, we show a new technique based on sort of this notion of approximate max information, which unifies the ideas of these 2 techniques into some sort of measure of how much information you have learned about how much information the output of the algorithm gives you about the data set. And that's all that I have to say about the techniques. We have various applications of these techniques, and one perhaps most interesting context is the reusable holdout. As I have mentioned, you cannot reuse holdout and still get the same. If you reuse holdout adaptively, you will not have the same guarantees. What we show that there is a way to implement the holdout to estimate to estimate the error of various predictors that will work, which will be reusable. And specifically, we prove the following theorem. It's, of course, informally. So given a holdout set, which consists of n IID samples, this algorithm can estimate the true error of a large number of predictors, which can be chosen adaptively, meaning I can choose a predictor on the basis of seeing previous performance of previous predictors, if few of those overfit to the training set. Here, we're using holdout set, but overfitting is measured relative to the training set. And of course, the devil is in the detail here. What are these few and large? So specifically, we show that the number n has to scale roughly as the square root of the number of hypotheses which overfit times the logarithm of the total number of predictors whose error we estimate times the tau square, which is sort of the accuracy of the estimate. And for comparison, if you just use the sort of standard way to implement holdout, which is by looking at the empirical mean, then you cannot provide, for this one, one cannot prove guarantees for which n scales better than linear in M. And you can see here the sort of the improvement is effectively exponential, of course, with this additional dependence on the number of hypotheses that overfit. So we show that this is not beyond this sort of nice theorem. There are at least some simple settings in which it indeed prevents overfitting. And we look at this very simple procedure, basically an illustration of this whole approach. And in this, we have a very simple algorithm. We start with some d-dimensional data set, which is with a binary label. And the algorithm which we are going to test will just pick variables which are have strong correlation with the label. And we'll then validate those correlations on the holdout set, meaning that we'll only keep those where the correlation is strong on both the training set and the holdout set. And then we'll check the prediction error of some very simple linear classifier, which is just the sign of those variables which have survived. Basically the sum of those variables with the sign of the correlation. So it's a very simple algorithm. We see, so when we test it on this following distribution, we just take 10,000 points in the training set and 10,000 points in the test set. Here we'll take, in this example, all the sort of features will be distributed from just independent normal distribution, normal Gaussians. And they'll be completely randomly labeled, so there is no hypothesis, there's no hypothesis which has true error better than 50%. But if we run this algorithm, okay, so the 50% is the error with this red line. The training set we sort of expect it to overfit because you select variables and then you test on the same data set, so it overfits. But here we show even if you use the standard holdout, the holdout will also overfit. Now, if we use it with our algorithm, we can see that the training set still overfits, but our reusable holdout sticks essentially to the correct error. And kind of to fully show that this works, we also have to look at the case where there are some variables which are actually correlated that we can also detect the true signal, and we do just that. We also look at the case where we plant some variables which are correlated, and those will be detected correctly. Again, this is another plot. So that's all that I wanted to say about this work for now. You can find me here if you want to know more. There are 2 papers which describe this approach. If you want to know sort of have a shorter summary, there is a paper in Science on this work. And if you happen to be at NIPS, you're invited to come to the workshop on adaptive data analysis, the first one, which will be organized by myself, Moritz, and Adam Smith, and Aaron Roth. Thank you.
First, before we go on to questions, we didn't see yet the next speaker. Are you in the room? No? So the 4th speaker, Michael, please prepare yourself because you will be the next speaker. Oh, sorry, you're here. OK. Sorry about that. I didn't see you. OK, so let's take some questions. now. Any questions?
Anyway, if you have questions
I
later,
have
I'm
a
around.
question.
Oh,
I
sure.
have a question. So you didn't describe in much detail your actual procedure, right? You alluded to the fact that it's
Yes.
related to differential privacy. Can you tell us a little bit more about it?
Sure. The procedure is actually very simple, based on sort of two ideas, and one probably more important than the other. First, when we know that the predictor whose error we're testing does not overfit to the training set, then we can just use the error on the training set as the response. So basically, as the estimate, so we can use the answer on the training set instead of the answer on the testing set, because we know that because it doesn't overfit to the because it's close to the testing set, which also kind of means that it does not overfit. So the second simple modification is, which helps in the adaptive setting, is adding a bit of noise, in which case we can add either a bit of Gaussian or Laplace noise to the answer, which also reduces, in some sense, the amount of information that is given back to the algorithm. And sort of the whole goal in the adaptive setting is make sure that the algorithms do not learn more than they need to learn about the data. So whatever they actually need, they should learn, but beyond that, we try to release as little information about the data as possible.
Okay, and so the way you choose the probability to inject that noise, for instance, is related with differential privacy.
Yeah, so if you want to have, especially if you want provable guarantees, you'll have to, it will depend on the provable guarantees of differentially private algorithms. And then, the parameters, yes, will depend on those.
Okay, any other questions?
Yes?
So in your graphs, I saw that there was a small spike at the start for the, I think there's a
both. Both.
So could you, do you have any reason why that actually happened and then it dropped back down to the original?
Yeah, that small spike comes exactly from this, from what I described, that if the error is close enough to the error on the training set, then you don't release any information. So there is a spike in the beginning, because in the beginning the divergence between the training and testing is still small. So we still report our reusable holdout still reports the training error, basically the training error instead of the error on its actual data. So it's keeps trying to hide its data from the algorithm. Great question.
Hangbui? Okay.
Any more?
Okay, we need to go to the next speaker. Let's thank the speaker again. It's a pleasure now to welcome Hong Bui from Adobe Research. He will talk about his work about efficient Thompson sampling for online matrix factorization recommendation.
Thank you. So this is joint work with a couple of other colleagues at Adobe Research, Jaya, Branislav, and also a couple of other people. It's really an international crowd here, one from University of Southampton in UK, and another person from University of Sydney. And this is also from a work that's going to appear in NIPS this year. The paper is, unfortunately, it's not out yet because we still have to do something for the final version. But it's going to be soon. We'll soon post it on archive. What is it that I want to talk about today? So let's go to recommendation system. Most of the people in this room are already familiar with it. The only thing that I want to emphasize in these slides is that there is actually quite a big problem for recommendation system, how you actually start from the code. So this is known as the code start problem. This is when there's very few data in your system and you have new users and new items arriving over time. So the focus of this talk is actually mostly about trying to address this code start issue. Again, think about a situation when you start from the extreme code, like there's literally no data in your system. If that's the case, then typically there is a problem of trade-off between exploration and exploitation. Basically, exploitation here is when you actually want to recommend the most relevant item to the user that just arrives in the system. On the other hand, this is just what the system thinks is most optimal at that point in time, right? And at the beginning, the system believes is very uncertain, and you should expect that there's really high variance about what the system belief is. So the system should also, be aware of that and try to do exploration as well. And exploration here means that you sometimes need to also, be a little bit more adventurous and then try to recommend the items that are just less known about. And when you recommend these items that are less known about, then of course you get more statistics about these items, and then you'll be able to build a better model for those items. Again, I mean, this is basically another way to look at this is that you try to avoid this so-called cocoon issue, where you kind of like only recommend a certain bunch of items, and you never get statistics about a large population of items. So you can see that in order to do this, then you actually the system actually has to maintain its uncertainty about the model, okay? And the model that we're talking about here is most likely is going to be a matrix-factorization model. So one of the technical questions that you're going to have to address is how you can actually be able to do online matrix-factorization. Okay? So, the way we think about this is that, well, let's think about recommendation, well, not as matrix factorization, but why do we think about it as online learning and sequential decision making? Okay? So the problem is like this. At time t, you are a user, a new user arrives, that's called IT. And then the action that the system needs to take is to recommend an item JT. Okay? And after that, the user receives a feedback, reward, and of course the rewards is based on some unknown distribution that you need to learn about. And the goal here is to actually optimize or maximize the accumulated rewards. It's also known as minimizing the accumulated regrets. So a really simple, very sort of like a simplest, dumbed down version of this problem is the Toniann bandit problem. And I'm sure that many of you here are already familiar with this. Here, like the input there's no input. You have to pick an arm or recommend an arm, and you get a reward, and then the probability about the reward according to the arm is distributed according to some unknown distributions. So there are various ways that this problem has been studied extensively in the online learning literature. So there are various strategies you can do this, and one of the popular way to do this is something called Thompson sampling. And what Thompson sampling does is that you try to do the following. You assume some prior on these parameters that actually govern the different arm. And then at each time t, what you want to do is that you want to randomly recommend different arms. Okay, so this is actually a stochastic policy. Okay, you randomly recommend different arms, and the probability that you want to recommend the arm J is equal to the probability that the arm J is actually the optimal given the information up to time t. Okay, and equivalently, you can implement this strategy very simple. As follows. First of all, you sample the probability of the parameter. You sample the parameters according to the posterior, and then once you get this sample, once you sample the parameters from the posterior, then you use that parameter, and then you just treat it as if that's a true parameter and recommend the best item according to that parameter. Okay. So it's very simple, and it works very well in practice. Now, so for matrix factorization bandit, the situation is a little bit more tricky. So again, we're looking at recommendation as an online and sequential decision-making problem. In order to apply Thompson sampling, first of all, you have to assume certain prior. Okay? So what is the reward prior? Well, people have come up with many different models and very interesting models, and this problem actually has been addressed so far before. So we just basically make use of a model called probabilistic matrix factorization. This is actually in a NIPS paper in 2007, and this is a graphical model for that prior. So basically, the latent features for the user and the latent features for items follow a certain prior, and then you have a hyperparameter for that. And the rating is basically, it's just basically a randomly put up ratings that you'd get from matrix factorization once you know U and V. Okay, so in this problem, then alpha and beta are fixed and tunable, and all of these are unknown parameters that need to be estimated. Okay, so if you're going to use Thompson sampling for this, then the strategy again is very simple. Assuming that you can actually maintain the posterior of the parameter over time, then you should sample according to that posterior, and then treat the sample as if that's the optimum parameter, and carry on. So the main difficulty here is how you can actually keep and maintain this posterior over the parameters. And the approach that we're using is we're using something called a regularized particle filter. So here's the picture of how you can actually use particle filter for Bayesian parameter estimation. First of all, this represents parameter space, right? And each of these arrows here represent like a point mass on that parameter space. So you start off with, assuming that you have a PT already, representing by, a bunch of point mass distribution there. And first of all, you reweight this kind of like point mass distribution according to the new evidence, and you resample. And then critically, the last step is that you actually have to perturb this resample point estimate so that you add more diversity to it. And this is called so this is actually called a move step, where you basically try to perturb these positions according to a kernel that is stationary with respect to the posterior at that point in time. Now, when you apply this to matrix factorization, basically what we want is that, first of all, we realize that, well, okay, there's no need to keep both the U and the V, all right? So keeping V alone is sufficient because it actually integrates out U. Another critical idea that allows for efficiency is that for this move step, in fact, it's actually necessary to only perturb the latent feature for the current user and the current item, okay? And you don't need to touch anything else. So even though that you actually with a particle, you actually keep the entire set of latent features for the entire users and entire items. However, when you're doing the update, you only have to touch the latent feature for the current user and for the current item. Okay, so this is really the key to efficient implementation of this idea. So how well does it work? Oh, well, if you just do a plain vanilla particle filter, then you see that there's a typical degeneracy problem for the particle filter here. That's in red. That's shown by the variance. And if you do Reusable localization, then again, if this is a simulation result, then the variance remains under control. This is the picture that shows that you can actually just do one iteration of regularized particle filter, and you get your result almost as good as 50 iterations of SGD. Okay. To give you, so how well does it work? Well, so we tried this on a bunch of data set here, and the idea is okay. So here, let's go straight to the results. So this is on a really small data set here, but the idea is that our algorithm here is, first of all, this is the regret curve. And it's sublinear, which is good. It basically shows that the system is doing the right thing. If you actually have a linear regret curve, then basically the system is not learning properly. Okay, so this is sublinear. It's almost as good as this thing in green here, which is the most popular baseline. This is actually an oracle, assuming that you know the most popular items in advance. Another thing is that as you vary the number of latent dimensions, and you keep the number of particles fixed to something very small. Here's we're only using 100 particles here. Then again, I mean, you have still very nice sublinear regret curve. And the story carries on for a larger data set, and so this thing seems to work very well. So in conclusion, to address the co-start problem, we'd like to be able to treat recommendation as a sequential decision-making problem. And one of the idea here is that we can actually use the Raziperchikolaei particle filter to maintain the post area. In future work, we'd like to work on the regret bound for this problem because we believe that the regret bound can actually be bounded. Thank you.
Any question for the speaker? Yes.
So do you have to keep 100 copies of the model rounds in memory at every step?
Correct. Correct. However, the update step is extremely quick because you only have to update for a current user and current item. So so in terms of memory, you really have to basically keep 100 copies of the model. You're right.
Okay, I will not take more questions. We're running a little bit late. Let's thank the speaker again. Thank you. So now we will finish this session with Michael Pacer from UC Berkeley, who will talk about, we'll just, okay. So Michael will talk about some points on graph, finitary Poisson processes, intervention, and first shot events. Ouais, bon, ok. Est-ce qu'il y a quelque chose que je pourrais dire? Non. On va faire une danse. On va faire une danse. Ouais. Excellent. La danse du vent.
We need to swap the... I think, yeah, that's the trick. Wonderful. All right. Today, I want to make some points on graphs. I want to suggest that we can model communication or message passing processes using structured point processes. If you don't know what I mean, the key feature is that it's going to be a system with n nodes or entities. Events are going to occur between these entities, and they're going to occur at particular points in time. The two central formal structures we'll be using are directed graphs to give us our syntax, that is, who talks to whom, and point processes to give us the semantics, that is, why, how, when the entities are talking to each other. Each of these frameworks is a powerful tool for modeling stochastic phenomena, and in unifying them, we gain a myriad of applications, not to mention some interesting theory. Some examples of the cases that have already been modeled by structured point processes include real-life communication in educational, judiciary, and negotiation settings, as well as electronic communication systems such as email and Twitter, in which they've been used to identify which individuals influence one another and to what degree, as well as to better predict which tweets are going to be the most popular. Structured point processes have also been used widely in finance for modeling security and stock markets, as well as being the basis of a wide variety of the innovations in high-frequency trading. They've been used to induce the structure of service and host dependencies over a closed network just from sampling packets at a single server, predicting failures in supercomputing and data centers, as well as to preemptively recompute cached items to avoid cache stampedes, which can occur if a recently uncached item is regenerated too many times because it's been requested in too short of an interval of time after being recently uncached. And in neuroscience, structured point processes have been used to identify the local structure of information representations in retinal and early visual areas, among many others. They've allowed for transforming control theoretic dynamics into plausible neural networks, neural signals for real-time brain-machine interfaces, and facilitated crosstalk between researchers in electrophysiology and mathematical models of neural spiking by providing mappings and constraints for the bidirectional relation between membrane dynamics and synaptic conductance and the rates of neural activity. With such a variety of applications, and there are many, many more, trust me, it should be clear that these are a powerful analytical tool. Today, I want to describe extensions to these frameworks, or frameworks like these, to include some probabilistic tool sets that enable modeling an even broader set of phenomena. Before going any further, we're going to need some background information. So rather than general point processes, I'm going to be talking about Poisson processes, which are a class of point processes for which the number of events expected to occur in some subset of the space is a Poisson random variable according to the integral of some rate function lambda. This rate function needs to be weakly positive, as there's no such thing as a negative event rate, and to be a proper Poisson process, it must have a non-zero rate for a measurable subset of the support space. In particular, we're going to be looking at marked temporal point processes, where the temporal processes, that is, the support space is the positive real line. And if the process is orderly, this has the useful property of being able to describe at all times which event is next. Because this treats events over the entire graph as a single process, we're going to need to consider marked Poisson processes where a mark is associated with each one of the events so that we can know which node of the graph each event is generated on. Some of the nice properties of Poisson processes come about when you are considering independent Poisson processes. For example, homogeneous Poisson processes, which have a constant rate and an infinite number of events over their lifetime, and non-homogeneous processes, which have some time points at which the rate is going to be different from each other. They both have the superposition property, where if two or more of these are independent of each other, the union of their events is also going to be a Poisson process, and that process will have the rate of the sum of the individual component processes. In particular, then, you can move on to self-exciting point processes, where the rate is depending on the time and marks of the particular events. These are also called Hawkes processes after their inventor. And that is, if you know the time at which all the events occur before t, then you know the rate function at t. And knowing that, we can use a conditional superposition property. That is, we know the rate function at that time for any of the processes, and therefore we can take the union of them. They are rendered independent because we know their rate, all the influences have been computed already. And the self-exciting part comes into play from the fact that these processes treat each event as inducing a new process when it occurs, and that process's rate is determined by some kernel, often associated with a mark. And that new process is then superposed with the existing processes, as I've now mentioned several times. So traditionally, Hawkes processes have their dependencies described between all of the marks, but if the induced rate is 0, then there's no effective dependency. We can let edges encode the dependencies where no edge means that it has induced rate of 0, and attach kernels to each one of those edges. So the kernels can be defined now over pairs of marks, not on each mark. And processes like these have a long history and are the basis of some of the recent machine learning applications I listed at the beginning of the talk. So what's missing? I've just described a very rich framework. So current models need something to get them started. That is, if you have no base rate, then there is no starting event. There is no method for pure forward sampling Hawkes processes on directed graphs, and there's no way to disable a node or to change its stationary properties based on the arrival of a single event, because edges are treated as stationary process inducers. And there's no in-use semantics for point interventions on particular nodes at particular times, at least in the sense of intervention, in analogy to that in traditional causal Bayesian networks, if you know about those, and don't worry if you don't. Our current work aims to address these points. So finitary Poisson processes are Poisson processes for which the entire history of the process, you can expect a finite number of events k. Because of this, they need to be non-homogeneous. And then to sample the number of events from this process, you just sample a random variable with mean, Poisson random variable with mean k. Note, because it's Poisson distributed, that means that some processes can produce no events. Regardless, all of these processes can still be superposed. This gives us a convenient way to sample from FPPs. We sample the number of events as Poisson with mean k, and then for each one of the events, its time is going to be the rate function divided by the expected number of events. We know this is a valid probability distribution because k, by definition, is a normalizing constant for the unnormalized distribution that we just integrated. And if it can't be integrated, then it can't be our rate function. This allows exactly sampling from arbitrary rate distributions so long as that distribution is defined and can be sampled from. And many standard kernels can be interpreted in this way. To sample from FPPs on graphs, we jump to the first event, which just happens to be on node Ni. We induce the finitary process from each of the edges leading out from Ni, according to that edge's kernel. We generate the entire event set based on each one of those processes, and then we union those events with the others that already occur on that node. And then we go to the next event and iterate. Sampling like this allows inference through techniques such as rejection sampling, MCMC, and approximate Bayesian computation. And sampling in these kind of complex stochastic cases is often the way that inference must be done. But to follow that algorithm, it'd be convenient to know the distribution of the first event. Fortunately, because we have an analytic form for the event time distribution, we can compute it. And it's that, and I'm not going to describe how you get that because I'm running out of time. Additionally, this allows for a nice semantic opportunity where we change the models, when that first event occurs. And that can be useful for modeling some kinds of systems where you have an acquired immunity from recovering from chickenpox, or when someone buys a particular item, no one else can buy, using a buy now button, no one else can buy it. Or say, when a node dies. So one of the reasons that FPPs have not been discussed before is that to get the cascades of events to start requires a non-zero base rate to bring about the first occurrence. But then that requires but that base rate usually is treated as a homogeneous or a periodic process that is going to have an infinite number of events. So we're going to introduce the notion of point interventions, which are valid point events that are treated as independent of the preceding point events. And once it happens, it goes unexplained. If you allow this, then you can have processes that are generated with zero base rates. And zero base rates allow pure FPP generative graphical models. So it'll help to understand this if you have an application, which I will draw from some of my work with Tom Griffiths on modeling human causal induction as structure inference from data embedded in continuous time. I'm going to show you a video that is a stimulus like that from an experiment by Dave Lagnato and Martin Spiekenbrink. In it, colored circles are going to flash on and off, as well as which indicate the seismic waves, A, B, and C. And sometimes a big white flash is going to happen that indicates an earthquake. And what people are going to want to, and if flashing bothers you, close your eyes for the next 15 seconds. So what people are asked to do is to judge the extent to which each of these events is the cause of the underlying earthquakes. Each person got a unique variable, or a unique video, and which was generated from one of 4 data generating conditions. So we're going to treat this as a structure induction problem. And in our model, there are 4 nodes, A, B, C, and E, with the associated point events. And we'll assume that A, B, and C are sets of point interventions, as I discussed, and that each is a potential cause of the earthquake, meaning that they are independent of one another. So this gives us a set of potential graphs with a uniform prior over those, a bunch of hyperparameters, exponential edge kernels. This gives us a likelihood, and we can infer a posterior distribution for each video. And people's responses were on the individual causes. So we need to take the sum of all of the graphs that include that edge from the cause to the other. Since we've generated a posterior from each one of the videos, we can then partition those into the sets that the condition that generated each one of those videos and take the sum over that, which then gives us the Bayes with FPPs here, predictions of the human judgments for each one of the causes, which has a average correlation per condition of 0.93. with the human judgments. So in conclusion, structured point processes are powerful models with a diverse set of applications. FPPs can be sampled using exact forward sampling, which can in turn be used for inference. First shot events allow for the meaning of the node to shift when a particular event occurs for the first time. Point interventions allow for zero base rates and pure FPPs over graphs. And point processes can be used to model human causal induction as rational structure inference. I want to thank my advisors and collaborator, Tom Griffiths, the Berkeley COCOSci lab, and in particular the lab mates Jordan Suchow and Jess Hamrick. And I want to thank the organizers and sponsors for bringing us together. And I'm happy to answer any questions both now and after you've had a chance to eat, because the point event of hunger can, I know, cancel many question-generating processes.
So with that said, is there any questions for the speaker? So it seems like you were right.
Wait, and we're hungry.
Okay. So the lunch session will end at 1:45. Please try to be on time. We have a tight schedule. So everybody, bon appétit. Let's thank the speaker again.